this lesson on equilibrium. Equilibrium is a condition where the reversible reaction, some reactions are reversible, and if you have a reversible reaction, the rates of forming the products is equal to the rates of forming the reactants. So if you have A produces B, and it's reversible, if you have a reaction in equilibrium, B will make A. It will appear that there's nothing going on, but on the atomic scale, A is making B continuously, and B is making A continuously. Remember from reaction rates, initially you have all A and no B, so the rate is 100% from A to B. As the concentration of A goes down, then the rate of making B slows down. So if this is a big long line there, this is a little bit shorter. And now you have more B, or you have some B, which means now the reverse reaction can occur, and you get a little bit of B going to A. It's not very much because the concentration of B is not great. Eventually, the concentrations, the rates of the reactions of A going to B are equal. Looks like an equal sign. The symbol for that is A is in equilibrium with B. What is in equilibrium? The rates are in equilibrium. Important to know that. The concentrations do not have anything to be with the other. You can have a whole lot of A and very little B, but as long as the rate of A making B and the rate of B making A are the same, then you can have that. Again, this must be in a definition of equilibrium in a closed system. The forward rate must equal the reverse rate. Then you have an equilibrium. Many systems do that. Many systems do not. If you burn a match or something like that, you are not going to be able to reverse and easily and get the carbon dioxide and the water produced to make a match stick. It does happen. It's called photosynthesis, but it's not easy. So now the mathematics behind the whole deal. If the rates are equal, then the rate equations must be equal. Assume that these are both first order equations, just for the sake of argument. So the rate is equal to K1 of the concentration of A, and you have the rate of K2 equals the concentration of B. Just looking at it from the reverse, we don't do reciprocal or anything for that. We're just saying the rates are equal. Size and dimensions doesn't make any difference. If the rates are equal, then you can set the two equations equal to each other. K1, concentration of A, K2, concentration of B. Well, let's solve for K and get all the concentrations on the other side. So divide by K2, divide by the concentration of A. So you get A's cancel out, and the K2's cancel out, and you get K1 divided by K2. Let's call that another K. Let's call it K is equal to the concentration of B over the concentration of A. The B are the reactants. So the K is the rate constant, K is the rate constant. We're going to be spending a lot of time with that, so get comfortable with it. There are many, many different types of rate constants, depending upon what application we're doing. So the rate constant is equal to the concentration of the products divided by the concentration of the reactants. This is a rate constant, and the rate constant stays the same, but it is dependent on the temperature. So it's a constant as long as the temperature is constant. If temperature changes, then the value of K changes. You'll notice on the homework, it'll give you at a temperature of 300 Kelvin or at a constant temperature. You don't need to do anything with that. It's just letting you know that, yes, you can use this concept. An example of writing a KEQ expression for the reaction H2 plus I2 is in equilibrium with 2HI. What you do is you multiply the things. The rate, the K, the constant, is equal to the reactants. Now you got two HIs, which is the same thing as HI plus HI. So it's HI times HI, which is concentration of HI squared divided by the concentration of H2 times the concentration of I2. The multiplication deals with if you double a concentration, you don't add to the value, you double the rate. So if you double the concentration, you double the rate. So it's a multiplication problem, not an addition problem. So it deals with multiplying concentrations. The K value, if K is greater than 1, we say that the products are favored. That means you are going to have more products than reactants as a rule. If K is less than 1, then the reactants are favored. The industry would favor something where a K value is greater than 1. So that's kind of like the example that we do there. If we do the reciprocal, if we write down this equation here in reverse order, 2HI is in equilibrium, H2 plus I2, then if we write products over reactants, it would be the concentration of H2 times the concentration of I2 divided by the concentration of HI squared, which is the reciprocal of this. So if you want to reverse the reaction and you don't want to come up with a new value of K, you just take the reciprocal of K. If K is 5 and the products are favored, then here it's 1/5 and the reactants are favored, or the products are favored still, so it goes less than 1. Sorry, the reactants are favored because it's less than 1. The concentrations can either be in moles per liter, usually if it's a gas, we talk about moles per liter, or molarity if it's a solution. If it's an aqueous solution, we talk about molarity. If it's a gas, you do moles per liter. If it's a gas, you got to pay attention to see if that's a 1 liter container, 5 liter container, or whatever. So you do have to pay attention. If it's a gas and they tell you how many moles are in the container, you do have to pay attention to that. The label of K by convention is none. It's a number. It's a ratio. So K is dimensionless or unitless, containing no values and no labels. So we just go with that, doing that. Find the value K, given the concentrations. Let's say we have, well, let's go with the same equation we have here. H2 plus I2 in equilibrium to form 2HI. If you're given that these are all gases and you have 0.5 moles of H2 and 0.1 moles of I2, and you have 2 moles of HI in a 0.5 liter container. So since we're talking about gases and moles and liters, you got to divide by the 0.5. So this is 1 mole per liter. This is 0.2 moles per liter. And this is 4 moles per liter. If I do the math right. Divide by 0.5. Doubling it, yeah, it should double everyone, and they are. And now you plug it into the expression, equilibrium expression, products over reactants. And plug it in. So it's 4 squared over 1 times 0.2. That's 16 divided by 0.2, which is 80. And no label, because we're finding K, and that would definitely favor the product. So this would be a good industrial equation to use. That ends this introductory lesson on equilibrium.